Hi everyone, my name is Ben Actis. This is Breaking Mobile App Protection Mechanisms. You can follow me on Twitter at @benraw. So a few things. My background, I started a research lab. I was doing mobile security work for 5 or 6 years. I also did a lot of network sensor work as well, so I'm familiar with looking at packet capture. Then I went to Lookout, where I got to work with Tim Strazzeri, which is awesome. I think he's speaking later today, and Emily, who's also speaking. I got to reverse thousands of Android and iOS malware samples. Then I went to Synac, where I helped build their mobile attacking toolchain. So how do you, at scale, look for vulnerabilities statically in mobile apps and dynamically by hooking APIs? And then most recently, I started at Facebook on the Red Team. At night, a little bit of troll on Twitter. And I started a side business called Cyber Merchants of Death, so I can kind of do various bug bounties as well. I do want to thank Tim, John Sawyer, and Caleb. They taught me a lot of Android skill sets, and if you don't like anything I talk about, please blame them, because they're my tutors. So my objectives at the end of this talk is I want to make you all be able to essentially laugh at all the emulator and root detection techniques that I commonly see in mobile apps. I want you to be able to laugh at any kind of HTTPS implementation because you'll know how to get around it. And also, if the devs are doing cert pinning or key validation, I'll show you how to get around that too. So in terms of the outline, we'll spend a good chunk on the root and emulator detection on Android. Then we'll dive into some of the iOS techniques. We'll go into cert pinning and key validation. It's a little Android heavily focused, but the same techniques apply to iOS that you'll see in the previous section. Then we're going to go through some debugging Android apps and spend a little bit of time on some basic patching examples to kind of reinforce some of these skill sets. So root and emulator detection. Why do we want root? When you're root, you can debug everything. That means we can change code paths, we can change values, which is great. We can inspect obfuscated code or code called by reflection. And we can also grab sensitive return values, which is really good too. You can also see all the internal files and /data com app name dir, right? So usually these, are out of scope for bug bounties, but they contain really juicy information, right? They might contain tokens, cookies, secrets, or other values that can allow you to change application flow. So one of the things I like to do is go in there, grab a bunch of data, see how they're doing the web authentication, and I can pound away at a web API, right? And you can also modify everything as root. So any kind of system file or setting, you can change. You can get root a couple ways. If you're using a real device, a physical phone, you can build AOSP from source and select an engineering or debug build if you really enjoy that. You can also unlock the bootloader and load a custom ROM that has everything all set up the way you want. You could root the device via an exploit. And I also want to state the physical phone is much faster than the emulator. When you're using an emulated device, you don't need to purchase a phone. For those of you like me, I have all the Apple laptops, you don't have to carry all the USB-C dongles. It's already rooted and debuggable. And you can actually speed it up on OS X and Linux by installing this Intel HAMX driver that helps in the acceleration. And it's also good if you break your test phone right before public talks. So why do we want to break these mobile app protections, right? The protection mechanisms are often an obstacle to kind of novice bug bounty hunters, especially if they're unfamiliar with the mobile domain. Even though these obstacles exist, if you can get around them, there's usually a bunch of additional bugs still in those mobile apps, right? So when you're detecting these, you got a few different cases, right? So typically it's really easy static string checks. More sophisticated developers could actually pull sensor data, which we'll get into. And then there's actually some academia things out there of how do you detect virtualization on x86 with QEMU artifacts. But typically it's one of two things: really crappy string checks, or the devs did their homework, actually read the Google APIs, and they're using something called safety net, which we'll dive into. So how do we search through these mobile apps, right? If you're unfamiliar to this domain, there's typically 4 tools, right? Your most novice-friendly tool is something called dex to jar. You take your APK, your Android app, all it is a zip, you unzip it. Then you use something called D2J or dex2jar, right? And that's going to produce a jar file from your classes.dex. And you can open that in JDBuoy. And it'll give you a Java-like view. If you're a little bit more sophisticated and you want to do kind of dynamic debugging and patching, you're going to use something called APK tool. And that gets you an assembly-like view out. You also have tools like Jeb, which can switch between your decompilation and your disassembly on the fly, and tools like IDA Pro, which allow you to do debugging and much more sophisticated parsing as well. But for a lot of this, we can use free tools like grep. So in this example, Jay Case wrote this about on his blog. He has a huge blog post on this one. And in this case, I'm using grep, the R command for recursive, and I'm going to search for a string I know that is of interest to me. In this case, it's going to be master password. And you can see on your far left column here, I can see every single time that is used in what class. So one of the tricks we're going to go through here in this little talk is, hey, what string should you look for? And then you'll go to that location in the code and we'll inspect it and see how it works. You can also, if you use Jeb, search for strings as well, right? Really nice. You can just go down in the lower corner there, search whatever encrypted value you may want, right? And it'll show you exactly where in the code that is, right? So in this case, what I ended up doing is you can also click on it and do a cross-reference, which is really nice. And you can see where it's first initialized and then where it's used as well, which is great. You can also do a search in IDA, right? So one of the things you can do is you go to your strings window in IDA Pro, click on the particular string you want, right? You can find where in the code base that is, right? Then from there, you can just do a Control X for cross-reference. Hit where it is with OK. And boom, you can find out right where it is. Okay. So no matter if you're using free tools like grep or professional tools like Jeb or IDA Pro, this is how you can do it. So static emulator checks by build props. So we have a few things here. So typically your build prop file is when you compile Android from source, it's going to have fill this with a bunch of different settings. I think I'm getting a little background noise, by the way. All right, cool. Anyway, where was I? So your build props are properties about the phone, right? And you're going to see things here such as hardware, fingerprints. One of the common ones is goldfish on the bottom. So prior to a few years ago, that was a huge telltale sign, and a lot of Android devs still use it, right? So if we grep through goldfish, you can very quickly, typically most of the time, figure out where they're doing the emulator detection. So here's what we do. We grep for goldfish, and I can see on the left here the wallet/util security utils.smalley file. So then I can go to that place in the code, and I can modify it as needed. So another thing they'll look for in build prop is information such as your model, product, radio, etc. And don't worry, I'll show you how to get around all these in a little bit. And also test keys in Android build. Here's what it'll look like in the code. Right? So in this one, you're going to see something that looks like build, fingerprint starts with generic, or fingerprint starts with unknown. Again, very blatantly stands out in the code base. And how you get around this is trivial. Since you're root on the emulator, you can just go to the build prop file and edit those. So it's looking for goldfish, change it to, I don't know, turtle or giraffe, right? Trivial. And there's additional checks it might do. So one of them is the get voicemail number. So there's something called telephony manager, and it's designed to get information about the phone, right? Like if you want to figure out what country your user's in. So one of the things you can do is this get voicemail number one. And on your emulator, it's a static number. It's always going to come back the same. Some devs can look for this, right? Getting around it, again, is really trivial. Just make a copy of your emulator binary, right? Open it up in a text editor, figure out what the appropriate, base 10 to hex conversion is for that number right here, and then just edit it. Boom, you're good. The check will fail. So static root checks. So here's the techniques I've seen. Typically, it's one of these four, right? They're looking for the presence of a binary. They're looking for some attribute, like a weird directory change. They're hashing a particular file, or they're relying on existing binaries, like exec or who am I. Searching for these, trivial, right? So they're going to be looking for bin su, xbin su, or the actual APK files that invoke some of this rooting behavior, right? Like superuser.apk or chainfile.apk. These are really easy to get around. You can just rename them, right? Super easy. Just here's what it looks like. So system app bin superuser APK, rename that not superuser APK. It'll fail to check if they're not hashing, right? Looking for SU and /sbin_su, rename it not SU, right? The binaries will still work fine. Next check, which you often see, is checking the system attributes. So when you usually root the phone, you have this /system directory, and it should be only read-only on non-rooted devices. But when you root it, some of the roots will leave it in rewritable. Devs can check this. Super easy fix. Just the commands right there on the bottom. Just change it to mount -o. RO means read-only, right? Remount read-only /system. You're golden. Doesn't look unusual then. Smart devs will actually try to hash the file. So they actually will go through all the iterations they can find on the internet of SU or superuser APK, get a hash of those, right? And then check for those. So you could get around this a few ways. You could recompile SU, change a little bit of it. It's going to have a hash that's not public. That's one. One of the steps we'll get to in the next section is you could actually patch out these or no-op these checks. Or we could change the value of a check in the debugger as well. You also have some binary checks too, which you'll see. One of these is, I often see, is there's a command called whoami in Linux, which basically returns your PID, what user you're running as. If you're running as root, or it'll try to invoke running as root, sometimes you'll get a different value. So one of the things you could do is compile a little app in C, make it so it never returns a value that would flag this. That's one. You could patch it out and check the binary, right? Or you could also modify in the debugger as well. Dynamic checks. So these are super rare, but it can be done. So devs could pull sensor data and compare it. One of the things I would do at my job at MITRE is I built a little tool that would check if I was running an emulator. The emulator always returns a temperature of 32 degrees Fahrenheit or 0 degrees Celsius, depending on where you are, right? So if I'm in California and it's 32 degrees Fahrenheit, I'm probably running on an emulator. Devs could do more sophisticated checks, like checking the number of contacts, calls made, SMSs, number of installed packages. That's really, really rare. But typically the best dynamic check out there is this Android Safety Net or Google Safety Net API. That's really cool. So what this does is whenever a dev uses this, it pulls down a special binary from Google that varies every few times, does a bunch of checks on the phone, measures a bunch of things, sends it back up to Google, and Google knows, based on your phone model and operating system, what's a realistic looking phone or a rooted phone or a non-rooted phone, and then returns that value back, right? I personally don't know how to get around this. The Pokemon Go reversing forums actually has some really good teardowns here. This is what safety net call would look like. So you're going to see some telltale strings here. The safety net service, the Google API state, you'll see. And the method in particular that starts this test is that AT test method on the bottom, highlighted in yellow. There's a phenomenal teardown of safety net on the link on the bottom there if you want to learn more, because that alone could be like a 60-minute talk. Okay, so TLDR here. Unless it's safety net, we can get around it either by patching or changing values by a debugger or just trivial little renaming things. The first link there is a great academic paper of the strings you want to look for. There's also a really good Black Hat talk that they went through all these techniques of root detection and showed how trivial you can get around them too. Okay, on to iOS now. So iOS, when you jailbreak an iOS device, there's roughly about 4 ways that you're going to detect this, right? First is jailbreak artifacts, right? Next, you're going to have non-standard ports, differences in the sandbox, and system modifications. And we're also going to touch a little bit on the app hooking via Frida and Cydia too. So these strings stand out. If you see an iOS app looking for bin bash, that can be a sign. Your iOS by default is not going to have bash, and you jailbreak it, you're throwing bash on there. Any references to the Cydia app or apt, which is the package management tool, that's going to be an indicator, right? Because on non-jailbroken iOS devices, you can't do package management like that. You're getting everything from the iOS store, right? or a trusted enterprise cert that's side-loaded on there. Any references to Pangu or your other jailbreaking tools, right, such as io.pangu.exe. The other ones you're going to see, they're often a check for mobile substrate, SFTP, or stash. Right? So if you see these, see if you can patch out those methods for those checks. The other trick you can do, which is an interesting one, is when you jailbreak an iOS device, you're communicating over SSH typically, right? Look for any code references to localhost 127.0.0.1, and then see if they're checking that socket, right? That's an easy check. So this is some neat stuff, right? So then there's also sandbox changes, right? So fork splits a new process, right? On your non-jailbroken devices, apps can't fork themselves, right? But based on some of the jailbreaks, you can actually do that. So one of the things the process will try to do is call fork. If that succeeds, then it's likely they're running in a jailbroken phone. There's also little file differences. So another common example is you shouldn't be able to write to the private directory. Devs will sometimes try to do that right. And if that succeeds, then they know, hey, something's changed with this sandbox and probably jailbroken. The next one is system modification. So this one's actually a cool one. So to make more room for all your jailbroken apps after the jailbreak, they take the applications partition and they make that like a symlink. If you see a dev checking for that in your assembly code, then you know that's one technique. And all these are gone into much, much more granular detail in the Mobile Application Hackers Handbook. So this is another neat one you can do here too. So to detect if there's function hooking, like if you use Frida or any of the other hooking tools, there's a few things you can do. There's a neat little binary called DLADDR, and how that works is essentially give it a pointer, and then that pointer it'll tell you where, a pointer to a process, and it'll tell you where that process originated from, which is pretty cool. Now on iOS, on a non-jailbroken device, your process is going to either come from, you're currently running one, system library text input, accessibility, private frameworks, or user lib. If it's anywhere else, then it's got to be a jailbroken device, or it's got to be hooked somehow. So bonus, you can also look for debugger detection, right? So if you see a call to ptrace or ptrace attached to NI, probably doing a debugger check. You can also do it with sysctl as well. And if you have any questions on this, please go ask Tim. He's giving a talk after me. He's much better at this kind of debugging detection than me. So how do you get around these, right? Same kind of countermeasures, which we'll dive into on Android in a little bit, is you patch out these checks, which I'll walk you through how to do. And you can patch it on Hopper. Hopper is about $100, I think, per license. IDA Pro starts at about $1,000. You can also see the Mobile App Hackers Handbook for a detailed walkthrough. And if you're new to ARM, because a lot of this patching on iOS is going to be at your ARM disassembly level, there's a great 2-day video course up on opensecuritytraining.info/intro to ARM. Also, Emily's giving a talk next too, and the OWASP mobile guide online is really good as well. Okay, cert pinning time. So intercepting traffic on mobile is actually pretty easy. My preferred approach is man-in-the-middle proxy. So I run OS X, so I just do brew install man-in-the-middle proxy. I launch the app, and then on my physical phone, I set the proxy. So I go to my Wi-Fi network, change it to whatever the IP address of the desktop machine I'm running the interception on, do port 8080, and then I install fraudulent cert, right? And I can see everything then. The cert pinning and key validation, right, or key pinning and cert validation, rarely implemented on a lot of mobile apps, which is sad, which is good. But I'll walk through how to go through it. One of the ways you can tell cert pinning is occurring is your man-in-the-middle proxy is going to fail. It's going to be say, hey, I can't decrypt this. If you see that, one of the things I do is I go in the /assets and the /res-raw directory. If you see anything that looks like a cert, you're probably doing cert pinning, right? So in this one, you see a truststore.dks file. And if I actually open that in a hex editor like ONO editor, you can see something that says like root certificate authentication authority, right? That's indication that's being loaded. And then I would look for that string in the code base and see where that's being cross-referenced. Other things to look for. So if the app's obfuscated, it might be a little hard to find these things, right? Well, the good news is even if it's obfuscated, you're still going to see the imports and certain exceptions in your code, right? So if you see these things that look like key pin store, key store exception, X509 cert, trust manager factories in your imports, they're probably doing something with the SSL there. To help you learn that, I recommend you go to the GitHub for OWASP, and also I think Munge has some good examples on his GitHub of how you could do cert pinning correctly. And if that's the case, you go look at that and then compile it and then see what it looks like in the pro-guarded or obfuscated view. That helps a lot. Here's what it looks like at a binary level. So we're in this check method. And you can see a couple things that will help you here in case you're unfamiliar. One, you're seeing a string builder with a string that's saying certificate pinning failure, right? So you have some clues there. Additionally, you're seeing later on in the file here, this append X509 certificate. So that's another clue that this is occurring here, right? And also the pin certificates for on the bottom. You're also seeing way on the bottom of this screenshot, the throw new SSL peer unverified exception. That'd be another clue. Right. And how we're actually invoking this is there's this v10.getCertificate pinning method, and then it's calling check, right? And that's basically saying, hey, is this the correct cert or not? So how do you get around this, right? So you can hook an API with, there's something called exposed that could do it easy peasy. One of the tricks you can do is you can just add or replace the cert with your malicious one, or you could patch out the code that's responsible. I usually do the patching. I find that's the easiest. So next we're going to go into debugging Android apps. So I have a couple of videos here which I'll play through. The first one, it's really short. I'm going to basically show you how to load apps into IDA Pro and use that Dalvik debugger. And I'll also cover how to set breakpoints, inspect local variables, watch variables, and decryption in the subsequent example. So let me load this up here. I'll full screen it. Hopefully you guys can hear.
Okay, this is a quick tutorial on how to use IDA Pro for Dalvik debugging. First step is I have the IDA command in my path right here. So if I just type the IDAQ, that will launch IDA Pro 32-bit. If I do IDAQ 64, I'll push the 64-bit binary. For our purposes, 32-bit's fine. So I'm going to do IDAQ, path to my APK file. And you can also directly do the particular classes.dex. But for this case, we'll do the APK. Hit enter. You're going to want to select the classes.dex file here. Note the size. Hit OK.
Cool. So that's a really easy way of loading it in IDA right there. There is a 30-day trial for IDA too. I recommend learning it. And if you're doing a lot of heavy mobile reversing, it helps a lot. So now we're going to go through a longer video here. And this one's kind of cool because I'm going to dive into everything of how you inspect what's going on the local stack, changing execution flow. And this comes from a really interesting malware sample where it's heavily obfuscated. And I had a hard time understanding statically what was going on. And I'll kind of walk through all of that here. Let's see, play.
So this is a tutorial how to do the dynamic debugging of IDA Pro. First thing you want to do is go into debugger options. Set specific options. Note you should have a proper path to your AVBX table here. If you're using multiple devices, you typically need to fill this in. To see this information, you can do it quite simply by AEB device command. This is the particular, it's a physical device, the serial you want to input there. And if it's an emulator, you'll see something along the lines of emulator hyphen 5555 or 5556. This information you can also fill from the manifest. You can just select fill from manifest.xml file. Pop-up will come. and you'll just point it to the particular APK file for item. You can also do it manually if you want a particular activity launch. And if you want manual things for ADB shell AM start command. Note that this is only for launching activities. If you want to do with a particular intent, you can't, it's a little bit more complicated. I'll cover that later. And that's it. Is it okay? Okay. And then you can do debugger, start process. And you'll see a few things I have here. I'd recommend playing around with the Windows settings so you like it. This is your local. These will have all your local variables currently. It doesn't only have
Hey, Ben.
Yeah.
the best way.
Looks like your screen is. Oh, never. Okay, sorry. The screen was frozen there for a second. We couldn't
All
tell.
right. We good?
Indicated line indicates at least
Yeah.
the breakpoint in this function com.qq.run. And it stopped right on this, move this value into constant 16. A few commands you should know. In your debugger ones, you have step into, step over, and then run until end of the return of the function and continue process. The Dalvik debugger is particularly finicky. One of the things you want to always keep in mind is the general register. It's pointing to all Fs. That means it's running in different code spaces you don't have access to. And you're going to need a breakpoint somewhere else along the execution. And so to catch that, essentially. I'll show you how to fix that state. So in this one here, a few commands you should know here. If I do this step into, which is F7, I will step into any functions. F8, step over, will step over them. So red indicates breakpoint. The cyan is the current line. And I'm just using F8 currently. I'm stepping over all these particular values. Note, after this line was executed, the change in color for this watch view, because I'm watching this particular object, be 0. To create a watch view, do a new one, I'm just going to right-click in here, do add watch, and then there's various expressions you can do. What's worked best for me is I cast as an object, asterisk, and then whatever the particular value. So we'll do V0 in this case. Boom, and it's populated. Right down there. Now, watching certain watch points will cause a Dalvik debugger to crash. So it's kind of an exercise in utility of type. So only watch the ones you absolutely need. If it does crash, delete that, move forward. So now if I do F8 here, this is the difference where we'll see F7 versus F8. If I press F8, will step over this function call and end up into this iGetObject thing. And I actually want to see what's going on. Also should be noted in IDA, you can comment easily by pressing the colon and semicolon commands. That's where I make these notes here. So if I press S, function F7. Now this is one of those cases where, okay, what did I step into? Notice that the general register is listed as all F here. So in this case, what I'm going to want to do is I can't see where I'm currently at. I'm going to do debugger, continue process, and I've stopped on a breakpoint. Now this is actually in one of the functions I care about. So what I'll typically do is before I end up here, I can click this, and this will take me to the method file or the function. And then I'll just set a breakpoint in that region, and that way I can catch myself. Okay, now look at this again. So I'm going to click in here. I'm going to do enable a breakpoint right here. Just in the event we end up with the FFF issue again. Step into it. Oh, this time I'm good. Keep going. I'm going to step over this one because it's just a call to the current system in seconds. So this here, another example, it's calling this A.E.B method. Step into it, note that I have a breakpoint set. So let's try stepping into it. I got a timeout. So in this case, you're going to have to terminate the process, restart it. And we're running again. So what I'm doing is I want to get back to right here. Now last time when I stepped into, I didn't, the debugger didn't respond in time. So I'm just going to do the, I have a breakpoint set within this function right here. So what I'll be doing is debugger continue process, which will then stop on that breakpoint. Cool. So same issue here. Timeout while waiting for reply. I'm going to now set another breakpoint a little bit farther down on this path and see if that fixes the issue. Another thing you can do when you get stuck in these kind of functions is you can do run until return. Runs until you get the method returns. Again, stepping over the call of the system time. All right, moment of truth here. All right. Boom, and we've stopped here. So when you get those JDB timeouts, play around with setting a breakpoint farther down in the code. So here's some interesting things where we can actually get values back. I'm going to continue this. So how this particular part of the Qigong binary works is there's a continuous call to this decryption function right here, this E.D method. And the result of this decryption is then returned and then stored in this D5 variable. And I've kind of just dynamically gone through and decrypted all of these. So if I step into this function here, here's all the wonderful things that are going on. I've pasted some intermediate values here. But I'm going to step over all of this. Note how in the watch view in the lower right-hand corner values are changing in the red highlighted text.
Cool. So that example is kind of interesting because, one, I think it's one of the harder to debug examples because they show all the ways the debugger can fail and all the kind of like gotchas that I never found in a lot of tutorials. So in this method here, I ended up finding a place where I was like, okay, you're doing some decryption and you're returning that value back. And once you identify where that is in a mobile binary, you find that kind of sweet spot where you can set your breakpoints, it doesn't crash everything. You can just trivially iterate through that and then like decrypt all your values and just comment it in there, right? And that's interesting because your decrypted values could be like the key to like a sensitive file or an API call that then you can hammer away at a web endpoint. So now that we know how to do that dynamically, right, I'm also going to look at how to patch some of these things too. Okay, so patching the app. So my goal in this one here is to make the Dalvik less scary, right? You really only need a small understanding of the assembly. We're going to go through about 4 different things here, what no operation means, remove object, return, and then how you invoke methods. So say we have a root detection somewhere. As from earlier in this talk, I grep with the R flag /bin su, and I find a bunch of classes. This loyalty security utils, device utils, and security utils again. I'm going to go to that place in the code. This one is something called isDeviceRooted method. And on your left, I have the assembly, and on your right, I have the Java. This is a tool called Jeb. If you're just learning this, highly recommend Jeb because you can do side by side, and it has a debugger like the IDA Pro example I just gave you. So first part on the left-hand side, when this guy starts, is it's moving this value into this constant variable. So just worry about these two. We have v1 and v0. The value of 1 is moved into variable v1. The value of 0 is moved into v0. This method is returning a Boolean value, true or false. So depending on the logic in the little method, it's either going to return the variable v1, which means true, or the variable v0, which means false. True is the value we want here. Even though the device is named like isDeviceRooted, true means it's not rooted. Now we're going to look at the actual checks, the conditional values here, right? So that same area on the left and the right means the same thing in the code, right? That if v2 equals 0 and return 0, same thing as everything on the left here. So how this works is it essentially has a list of strings it's going to be looking for on the local disk, right? And if those are there, right, it's going to set a value, v2 is equal to 0. And if v2 is equal to 0, it's going to end the function early and say, hey, something's false, this device is rooted. Now, here is that same comparison in the actual Dalvik disassembly. It's saying if equal to 0, value v2. If that's true, go to condition AA, which is then return, right? So that second line in the middle, the move, that's only if it thinks the device is not rooted, right? So we want to get that return value. So it's pretty easy to do this, right? So on the left is the original code. It says, hey, is this equal to 0, right? If it is, go down to that condition v1, exit early. Your phone's rooted. If it's not equal to 0, move v1 into v0, which makes that equal to true, right? And then return. So we can do this a few ways. You can just write no op, literally like delete it, just write no op means no operation. Then that way there's no check, and you end up in the move, which returns true. Or there's other ways you can do it, but I think that's the easiest one. Then you rebuild the app with apk tool b, and then you'll have an unsigned app in the /dist directory. Then you got to sign it. With key tool, super easy, just copy and paste this in there. You have a private key now, and you're going to sign it. So signing it, it's with the APK signer tool that's usually included with the Android Studio. I found out actually the most recent one forgot it, so actually just go to that link on the bottom, you can get it. And that's it. So let's do a little bit more complicated example. I think is the last one we'll have time for here. And this is a isDeviceRooted method. So what this is doing, again, the code on the left is the same as the code on the right. It's calling this deviceUtil.isDeviceRooted method, right? And then if that condition's met, it's going to kill its process, right? So what we got to do is essentially no-op all of this or delete all this, because we want, this method doesn't return anything, right? It basically does a check. If it's rooted, kills my process. So if it just returns nothing, we're fine, right? So easy way of doing this. Same thing. So here's what it looks like in the the Dalvik assembly. We're going to see a call to isDeviceRooted. Based on the result of that, it's either going to call the get the process and kill process. So super easy. You could either delete all this and just return void, or you could do a combination, do no-op, 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 then return void. Doesn't really matter in this case. Should be noted though, when you sign an app with your own signer, it's going to have a different signer, right? Different signature. Some devs do check this, but again, they're checking it. We can patch out the same check, right? So this one, this Boolean method B, it says, if it's not equal to this particular value, then go to this point. Again, you could just no-op that out. So again, trivial check. For learning Dalvik, there's some great resources right here. Yeah. So any questions, let me know. I'm going to exit out full screen in a second here. My Twitter is @benra. Email ben@cybermerchants, the death works fine. And yeah, I guess I have a few minutes left here, and I'll take questions. So let me go to Zoom.
Yeah, I think we might have time for about one question or so. I know that early on in your presentation, someone asked if you suggest using an emulator or...
I would start with an emulator, honestly. So like if there's financial concerns, start with an emulator. And then if the app's detecting it, then go and get a cheap $50 Amazon phone. Tim, look at Tim's GitHub. He has a nice root for a lot of those, and they're often on sale. I would say with the exception of maybe some of your banking apps and your really popular apps, yeah, I think you'll be really good to look at. I do the emulator. You can also do an x86 one. That's pretty fast. The nice thing about the phones is if you want to get really crazy with things, like you can get a Nexus phone and actually change part of the Android source code to make things easier for you. That's kind of way more advanced kind of techniques out there.
Cool. So I think that's all the time we had for this presentation of Ben's, but we'll have Ben back again.
I think in an hour or two.
Yeah.
Yep. Cool. Thanks, everyone.
Yeah, thank you, Ben.